In section 2, let's take a look at some events in more detail, in particular, focusing on multiple events. So the first is the complement of an event. So the complement of an event is the event that event E does not happen. Okay, so when we use the notation for the complement of an event, pay careful attention. It looks very similar, but it has a little line above. So E with the line above, that's the complement of event E. And so to find the probability of event, the probability of the complement, we do 1 minus the probability of the event E occurring. Okay, and also notice that the probability of event E occurring is also found by doing 1 minus the probability of the complement. Right? So all of those are connected together in that sense. Now, when looking at two events, we can determine that two events are independent events if the probability of event B occurring is the same whether or not event A occurs. Okay, so two events are independent if the first event happening does not affect the probability of the second event happening. Now, we take this and apply this to the formula for the probability of two independent events occurring. And we identify that as probability of A and B. So if A and B are independent events, then the probability of both A and B occurring is simply found by taking the probability of A and multiplying it by the probability of event B. Okay, so let's take a look at an example of events that are an event that is independent. So we are conducting an experiment by flipping a coin and determining if it lands on heads or tails. So we want to determine why flipping a head or a tail with a coin are independent events. So the reason these are independent is because the flip or the outcome of each flip is not affected by the previous outcomes. Okay, so in this case, if we think about flipping a coin, there's two ways you can think about this. So the first is that if you flip a heads first, the coin is not going to remember that it's already flipped a head, so it's going to change what it does, right? The coin has no input on what the outcome is going to be, right? Whatever the coin comes up, it comes up, right? The second thing is that as you flip a coin, you're not changing the coin in any way that would affect the probability of this second flip. Okay, so it's not like you're flipping the coin or you're bending it or you're damaging the coin in a way to force it to land a certain way or to change it to a certain way. So those are ways you can look at that. So now, what's the probability of flipping a head? Well, in a coin, there's only two outcomes that are equally likely, and the head is one of those two outcomes. So the probability of flipping a head is 1 out of 2. So what is the probability of flipping two heads in a row? So we can identify this as probability of flipping heads and head, right? Now, because we already stated that that the coin flips are independent, then we can use the formula from above in that the probability of flipping a head and flipping another head can be found by simply taking the probability of flipping a head and multiplying by the probability of flipping a head. So 1/2 times 1/2, which is 1/4. So the probability of flipping two heads in a row is 1/4. Now, we can also talk about two events being mutually exclusive. So two events are mutually exclusive if those events cannot occur at the same time. So using this, we can use this to help us find a special case for the probability of event A or event E occurring, event A or event B occurring. So the probability of event A or event B occurring is the probability of event A added to the probability of event B and subtracting the probability that event A and B both occur at the same time. So the reason for the subtraction is we are removing any probabilities that have been, or any events that have been counted twice in either the first two individual events of A and B. So when event A and B are mutually exclusive, then the probability of event A or event B is simply event A plus event B. And the reason being is that when the two events are mutually exclusive, okay, then the probability of A and B equals to 0 because they can't both occur at the same time. Right? So that's why with the mutually exclusive events, we just have a special case of the OR probability here. So in this example, we're going to look at an experiment that's conducted by drawing cards from a standard deck of cards. So if you're unfamiliar with the standard deck of cards, we have 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with an ace, the numbers from 2 to 10, and then a jack, a queen, and a king. Okay, and so we can identify probabilities by determining how many of each type of cards we are drawing from this set of 52 cards. So the first is explain why drawing a card that is both a king and a queen is mutually exclusive. And so the reason why that's mutually exclusive is because you cannot draw a card that is both a king and queen. So if you look at our standard deck, you notice that our standard deck only has either queens or kings. There's no cards that are both a king and a queen. What about drawing a card that is both a king and a heart? Why that is not mutually exclusive? And the reason that is not mutually exclusive is because there is a card that is both a king and a heart. Specifically, the card is the king of hearts. So when we go back, you see the king of hearts is this third one right here, and the king column, that is the card for the king of hearts. So it is possible to draw a card that is both a king and a heart. Now, let's find the probability of not drawing a king. So not drawing a king is the complement of drawing a king. Right? So we can think of this as probability of not king is equal to 1 minus the probability of drawing a king. You can think of it like that. Right? Well, what's the probability of drawing a king? Well, there are 4 kings out of the 52 cards that we have. So 1 minus 4 out of 52. And if we subtract 1 minus 4 out of 52, then we can get that probability. So since we're subtracting fractions, we can write 51 as 52 over 52 minus 4 over 52, which is 48 over 52. And that reduces down to 12 out of 13. So the probability of not drawing a king is 12 out of 13. So what's the probability of drawing a king or a heart? So probability of drawing king or a heart. Well, this is the OR probability, so we're going to use this formula up here. And the probability of drawing A or B is probability of A plus probability of B minus the probability of A and B. So probability of king or heart is the probability of the king plus the probability of a heart minus the probability of king and heart. So the probability of a king was 4 out of 52. The probability of a heart, if we look back at our list, there's 13 hearts out of the 52 cards. So 13 out of 52. And we want to subtract the probability that we draw a king and a heart, or the probability of drawing a king and a heart, and there's one of those. Again, we subtract because it's possible that you can draw your, well, we're subtracting that 1 out of 52 because that has been counted both in the king list and in the probability of the heart. So we want to subtract that so that we don't count it twice. And this leads us to 16 out of 52, or 4 over 13. So the probability of drawing a king or heart is 4 out of 13. What is the probability of drawing a king or a queen? Well, remember, the king and queen are mutually exclusive. So because of that, we're going to use the shortened version, the special case, which is just the probability of A or B is probability of A plus probability of B. So the probability of a king or queen is simply just the probability of a king add to the probability of a queen. Again, we don't have to subtract because there are no cards that are counted twice in these lists since these are mutually exclusive. The probability of each is 4 out of 52, which gives us 8 out of 52, and this reduces down to 2 out of 13. And now let's take a look at some special cases we refer to drawing with replacement and drawing without replacement. Okay, with and without replacement. So with replacement means that once we draw the cards, we're going to put the cards back into the deck and redraw again. Okay, so now we want to, if we're drawing with replacement, what's the probability of drawing a king and then drawing a heart? So now this is not the probability of king and heart. Okay, so probably a king and heart. So going back, we're going to use the probability of events here. What's the probability of A and B is the probability of A times the probability of B. Okay, so what's the probability of drawing a king and then a heart? That's the same as probably drawing a king multiplied by probability of drawing a heart. Well, to draw a king, there's 4 out of 52. And to draw a heart, because once we put the card back in, there's still 52 cards left in the deck, so there's still 13 out of the 52. Okay, so that's what we have there. So we can do 4 out of 52 times 13 out of 52. We get that. Now, what we want to do is convert it to a decimal, convert it to a fraction, which is 1 out of 52. Okay. Now, in the last example here, we see that we're going to draw without replacement. And when we draw without replacement, that means that after drawing the first card, we are taking that card out and we're not putting it back in the deck, which means that there are less cards in our deck now. Okay, so what's the probability of drawing a king and a heart? In this case, we start off the same. This is probability of king multiplied to the probability of a heart. And we can say after drawing king. We have to be more specific in this case because now we are not replacing the card. So the first card that we draw, the king, probably is still 4 out of 52. But what's the probability of drawing a heart after we draw the king? Well, now there's still 13 hearts left, and now there's 51 cards in the deck. And again, the reason why there's 51 cards is because we've drawn one card out and left it out of the deck. Okay, so 4 out of 52 times 13 out of 51, and that gives us 1 out of 51. So the probability of drawing a card with and without replacement are going to lead to different probabilities.